Hello, and welcome to the video. Today, we are talking about RAID arrays. So, RAID stands for Redundant Array of Inexpensive Disks. It was created in comparison to the current standard, which at the time was SLED. SLED was also an acronym, and it was kind of the opposite of RAID. SLED was a single large, expensive disk. So IT companies would go out and buy one really, really good hard drive. But if that hard drive failed, they lost everything. So they came up with RAID, right? Redundant Array of Inexpensive Disks. So they would go out and buy, 5 different really cheap, really inexpensive, low-quality drives, but they would make them redundant. So if one of them failed, they didn't really care. And this proved to be the dominant strategy. It was cheaper and more effective. Your data was safer in a RAID array than it was with a single, large, expensive disk. So today I'm going to teach you a little bit about how to make a RAID array and how they work. So RAID arrays are actually not just one thing. There are different levels of RAID arrays, and each one has different levels of redundancy. So we're going to be talking about a couple of them. I'm not too familiar with all of the levels, but I'll give you all the ones that I know. So first off is RAID level 0. So RAID level 0, if we imagine we have 2 drives here, if I remember correctly, is data striping. So RAID level 0 doesn't actually have any redundancy. But what it does is it takes the drives and it chops them up into these little stripes. All right, and let's say this drive is larger than the other one. Well, it stripes it, and each stripe gets its own little identifier. So this will be 1, and 2, and 3, 4, 5, and so on. And so RAID level 0 connects all of these drives together. And by adding them up, they're going to be equal to one really, really large drive. That's the sum of both of them. And so the advantage here is that you can take 2 smaller drives and combine them into be a bigger drive. And so the data, right, if you imagine this really big drive, we call this a virtual disk because it doesn't actually exist, right? These are the 2 physical disks, which comprise a really big virtual disk at the bottom. And so each section of this virtual disk corresponds to the physical parts here. So when I do a write operation on the very first memory address, it'll write it over there. And when I write it to this one, it'll write it over here. So that's RAID level 0. It's called data striping because it sort of cuts the hard drives into stripes. So next up is RAID level 1. And now that we are, RAID level 1 is sort of the first level of redundancy. And it's pretty simple. It's just copying the drive. So whatever we have written here gets written again over here. That's it. It just copies the data from the first drive to the second one. So really, again, these are the physical drives that you physically put in. And the operating system is running on, right, this virtual drive. And so when I'm writing some data in here, it'll get written both to this hard drive and to this other hard drive. So that's RAID level 1. So this is full data redundancy. You lose a drive, nobody cares, right? Because you have a full copy of the data. And so the operating system will work like normal in the virtual drive here. And it'll think, in all these scenarios, it'll think that it's running on a real drive that is really however large it is. When in reality, it is being passed off and written to multiple other physical drives. So RAID level 1 is just full duplication, right? Everything gets written down twice. And this means your write operations are a little bit slower. And it also means that you have half the capacity of the drives you actually bought. So you're sort of, it's twice expensive to buy memory because you have to buy twice as much for the same amount of memory. So someone came up with a solution. They said, well, hold on a second now. We have this really special property of XOR. And I think I have a cool way to use it to get us a little bit more efficiency than 50%, right? Half of our drives being cut up. So they came up with this solution. This is RAID level 4. Okay, RAID level 4. RAID level 4 does something a little sneaky. So it also does data striping, right? So it cuts up this first, our virtual disk here. Right, and so our physical hard drives are also cut up. But this guy is special, okay? He's special. So we still have, again, each stripe gets its own identifier. 2, 3, 4, 5, 6. And you can imagine, it goes on and on and on, but I'll only show you 6. So 1, 2, 3, 4, and 5, 6. So here's the sneaky part, where they keep data redundancy, and they get to use more drive space. So let's say in this first stripe, they go and they write the byte 0. Okay, I'll put a little slash through it. And then, they have 1, 1, 0, 1, 0. Okay, so what we really care about is we're going to look at slice number 1 and slice number 4. Now really these slices are bigger than a single byte, but I'm showing you the principle that they use. So we have a 0, and we have another 0 here in stripe 4 and stripe 1. So over here in our special drive, this is what it calculates something called a parity. And this is what we call a dedicated parity drive. So it does the exclusive OR operation, right? Also called XOR, and you might also see it like that. So it calculates 0 XOR 0 is going to be 0. Boom. And then it does it for every other stripe in the drive. Or I should say for all of the stripes, not every other. And so 1 XOR 1 is also going to be 0. 1 XOR 0 is going to be 1. So what we've done here is we've calculated a parity, and we've stored it in this extra drive. Now you'll notice that we have 3 drives, and we're getting to use 2 of them in our virtual disk, right? So we went from 50% efficiency to 66.6667, right? Infinite sixes. So we now get 2/3 of the drives we buy can be used for storage. But how do we keep the data redundancy? And why does it matter we calculated this parity here? Well, let's say we lose a drive, okay? So I'm going to erase the data in this second physical drive here. All right, so now we lost the data, we don't know what it is. Not good. However, we can use the parity we calculated to go backwards. If we try to reverse the operation, we say 0 XORed with something also equals 0. Well, we know that if this here is a 1, then 0 XOR 1 is 1. So it can't be 1. But 0 XOR 0 is still 0. So we know this byte has to be a 0. We do it again. 1 XOR something is equal to 0. So we know this has to be 1. And finally, 1 XOR something needs to be 1. So this has to be a 0. And so that's how you can use parity to rebuild lost drives. So when you have a drive die, it's really no big deal, because you go and you look back at your parity drive and you calculate, all right, here's where, here's the data that's missing, here's what went wrong. So now you can build this virtual hard disk with 2 drives and only need 1 drive extra. So again, we went from efficiency of 50%, right? You only get to use 1 out of the 2, to now 2 out of the 3, or 2/3. And this can be extended to even longer sequences, where let's say, instead of just having 1 drive, we want to use, I don't know, here, 4 drives, or 5 drives even. Well, we have our special parity drive at the end. And so now if it's, 1 XOR 0, XOR 1, XOR 1 is equal to, let's calculate it, right? 0, 1, so this will evaluate to 1. 1 XOR 1 is 0, 0 XOR 1 is 1. Okay. So now, let's say we lose one of these drives. Okay, so we don't know what this third value is. Again, we go back and we just calculate this in reverse. So we say, we know these two, we know this evaluates to be 1, and we know that this XORed with something XORed with 1 is equal to 1. So we have to figure out what this thing is. And we just look at it, we think about it, and we say, okay, we know that if it's a 1, then this whole thing is going to go and resolve to a 1. Because this evaluates to a 0, and 0 XOR with 1 is going to be 1. So that's how you can rebuild a drive and get your data back with parity. And so you saw there, we were able to use 4 drives to create one really big virtual drive, and we only needed 1 extra drive for parity. However, all of that parity is stored in that one really special drive. So something could happen to it, or it could never really be used. That's the other sort of big problem with RAID level 4, is that 4th parity drive just kind of sits there, where the data, gets calculated, gets shoved in, but you never really do any read operations. And so a lot of the read operations get concentrated on the drives that are part of the virtual disk, and not really to the parity drive. So you kind of want to spread out the wear and tear on your hard drives, especially with hard disk drives where it's actually a physical spinning disk with a little reader on top. You want to try and spread out the wear and tear. So this is what RAID level 5 does. So RAID level 5 is very similar to RAID level 4, where it does data striping, and it calculates parity. However, calculates parity in a very special way, where now, it still creates a really large virtual disk, and we still get 2/3 of it. However, the parity moves around from drive to drive. So in the first one, the parity will be over here. So the first stripe in each disk, the parity is calculated into the last drive. But then, for the second slice, it gets calculated into this drive. And the third gets calculated over here. And, if there were a fourth, it will loop back around and go back here. So we're able to spread out all of those read-write operations and calculating parity along all of the different drives. And so this would be 1, 2, 3, 4, 5, and 6, right? And so on. So we're spreading out all of the parity calculations across all of the different drives. So if any one drive dies, right, let's say we lose the left drive. We now have one piece of stored data. Right, I'll cover this up. We have one piece of stored data and the parity. So we could do that XOR operation to read it back. Same thing here, right? The parity is just stored on a different drive. We're here, we can calculate it again. right? We can do that XOR what is the thing that's missing that we need to result in whatever the star is. And this final stripe, we haven't even lost any data. That final stripe was a parity stripe on the first disk. So when we lost it, well, we just lost some calculation we did on the real data. The real data is still there. So there's no problems on that third level of stripe. So yeah, that's RAID level 5. Very powerful, very popular. Now there is, of course, an issue. See, every time for RAID level 4 or 5, when we're doing this data striping and we're rebuilding the disk, doing all of these XOR operations, you can imagine, right? In this example, each stripe only stored a single bit, right? Just a 1 or a 0. But in reality, it's going to store much more than that. And so when you go and rebuild these drives and do all these calculations, you have to read through the entire contents of all of your drives. And that significantly increases the likelihood a second drive fails. Right? If your first drive fails after, normal wear and tear, well, now you have to go through and you have to read all of the other drives in their entirety to rebuild the data that was lost. And that could result, it increases the risk of a second drive failing and you actually losing important data. And that can be pretty scary. And so they came up with RAID level 6. Right? And I'm not going to draw the virtual disk. I hope you get the idea by now that, there is all the drives are combined where the data stripes of each drive gets put end to end to represent in a virtual disk where the actual operating system and user space is. Okay. So now we have 4 drives. And I should note RAID level 5 requires 3. You can't do it with less than 3 drives. And RAID level 6, RAID level 6 needs 4 drives. So RAID level 5 needs 3, RAID level 6 needs 4. Because RAID level 6 does something very similar to RAID level 5, except a little bit extra. It also has data striping. It also distributes that data striping among the drives. And, it also has parity and distributes that parity among the drives. However, the reason it needs 4 is because there will always be 2 parity bits. So, right, you'll have your first stripe, and then your second. Then you'll have the parity bit, which you calculate, and then an extra bit over here, which you calculate not with an XOR, but there's an algorithm that you can use to calculate an extra bit of information. Now, that algorithm could be video all on its own, so I'm not going to spend time on it, explaining it, or going over it. But this is essentially what RAID level 6 does. It gives you an extra bit of parity, and it also, again, distributes it through the drives. So you don't need to worry about everything being concentrated, right? The load of these calculations and the read-write operations get distributed out. So yeah, that's RAID level 6. It's kind of like RAID level 5, except it stores an extra piece of parity. In the case that one drive fails during normal operation, and then a second drive fails while you try to rebuild, RAID level 6 doesn't care. It'll work anyway. And of course, again, the write operations will be a little bit slower, because now you need to calculate 2 bits of parity for every bit you write. But the trade-off is well worth it, because you are now very secure and your data is very redundant. You're not going to lose any data. The last things to note are the sort of naming conventions, because there are a lot more than RAID levels 0, 1, 4, 5, and 6, right? Those are the ones I covered. There are RAID levels 2 and 3, which I'm not familiar with, and there is two other common RAID levels, which I think are RAID levels 10 and 50. And I'm realizing now I must have mixed up 0 and 1, but that sort of convention of like 10 and 50, they just take RAID level, we'll go with 10 because it's the more popular one that you might run into. They take RAID level 1 and they combined it with RAID level 10. So in that case, it's data striping with a complete copy. And you can do this across multiple drives. So usually it'll be like 1 plus 0, and sometimes that plus is omitted, and so it's just 10. The last thing to think about is whether you're running a... Oh gosh, I can't use the black marker. It's running out. The last thing to think about is whether you're running a software RAID or a hardware RAID. And there's a difference. So there is a type of controller, a little chip, called a RAID controller. And the RAID controller is responsible for keeping track of all these disks and presenting them to the operating system. So the way it works is really, really nifty. So we have a little setup here. This is our computer. Here are the drives. So we'll say, HDD. Right? Let's say you're using some hard disks. It could be an SSD. Doesn't really matter. Here's your CPU. Here's your RAM, and maybe you have a GPU as well. Okay. Well, on a normal computer, you would plug these all in, and they would get to communicate directly with this hardware. But a hardware RAID controller, right? So hardware RAID, plugs these guys in to this intermediate. This right here is the very important RAID controller. So these guys get slotted into this chip, and out of it comes a single drive. So, you have the little, what I think they're called SDA cables. You plug them in to this controller here, and out comes a singular one. And so this RAID controller would have a little onboard computer, and it would do whatever RAID level you set it to. And so the computer thinks that you're only plugging in one drive, right? It only sees one cable come in. And it'll, when the CPU wants to do a read operation or write operation, it'll just send that operation to a single cable. It thinks there's only one drive. And then the little onboard computer in your RAID controller will then go and assign all of these write operations to all of your different hard drives. Right? So this RAID controller creates the virtual hard disk. And the physical drives get hidden behind it. So the computer has no way of knowing. So all the other components have no way of knowing that they're not talking to a physical disk. And so you might not see this at a at-home setup, a home lab, but it's more common with real data center servers. They'll have a physical RAID controller for hard drives to get plugged into. The other way to do it is with software RAID. So in software RAID, right, you have your hard drives, and you have your little CPU, and your memory, right, RAM, and these guys will directly connect to the actual hardware on the computer. And what happens is, you have one drive that's running your OS, and this operating system will go out and tell, the CPU to make the, correct write operations to these other drives. And so in software RAID, right, there is no extra physical components. It's just your really special drive, whichever one it is, that's holding the operating system, is going and telling the physical components, hey, write over to this drive, write over to that drive, and it sort of does it by hand. Now, one of the disadvantages here is that it's going to be a lot more difficult to rebuild your system, even if, let's say, you're doing RAID level 1 or RAID level 0, where you have the complete disk copying, right? A complete copy of the disk. Well, even so, you're going to have to go in and change the boot order if that drive fails. And if you're doing something like RAID level 5, you're in a lot of trouble. 4, 5, or 6. Because if one of those drives dies, you don't have a drive that's able to actually sit there and boot up. Especially with, again, 4, 5, and 6. Because remember, the data is distributed. It's over stripes across all of these disks, and some of the data in those disks are not, isn't true data. They're parity data for redundancy. So, usually, to have a RAID controller, a physical chip RAID controller, is a lot better. It'll be a lot easier because if a drive fails, you can still boot the machine up, no problem. You can start the operating system, get in, and as a user, you can go and have some warning that says, oh, a drive died. Whereas if you're doing a software RAID and a drive dies, you can be in some real trouble. So overall, it's a little bit better. Of course, it's more expensive. But if you're someone who's just at home, software level RAID will be a great job for you. So yeah, that's what I have to talk about today. It's RAID arrays, how to build them, how they work, a couple of the different levels that are commonly used. RAID, I think 5 and 6 are the most popular. Really 6, super popular. And then RAID level 0 or 1, whichever one is the full copy, is also commonly used. So yeah, that's all I have for today. I hope you guys learned something and enjoy learning about how data redundancy is done on a data center level.